I continue with section 1.1, then section 1.2. Taylor's theorem in more than one variable. Copy one. Taylor's theorem in two variables. Let omega be a rectangle in R2. Yeah, rectangle. A, B, cos C, D in R2. Yeah, rectangle. A, B, C, D. Yeah, this rectangle doesn't include the boundary. This way. And let function f be a function from this set. This function has partial derivative of order from 1 to n plus 1, and all the partial derivatives continuous on the rectangle. Sorry, this function. Okay, now in the rectangle, take 2 points. Yeah, take 2 points. This one. X, Y. Take the second part. X plus H, Y plus K. Second part. Okay. Then function value at X plus H, X, Y plus K. Okay. Yeah. Here, X and Y, they are considered to be constants. H and K variables. Now, this function can be expanded into polynomials. Yeah, summation I from 0 to n, 1 over I factorial, then partial derivative with respect to x, plus k, partial derivative with respect to y, then power I. Right? Yeah. F x y. Then plus Euler term. Euler term. The Euler term now is where the Euler n, yeah, h, k, is 1 over n plus 1 factorial, then h partial x, k partial y. Then here the power is n plus 1. Apply this power to function n. Then plug in a point. This point, okay, this point is x plus theta, h, y plus theta. Okay, what is theta? We don't know. Theta depends on many things. Depends on x, depends on y, depends on h, and k. Also depends on function. But one thing is sure: a between 0 and 1. Okay. All right, now let me explain this notation. Yeah, this notation. Here. Okay. H puzzle X. What is notation means? Okay. When I is 0, okay. When I is 0, then power is 0. So something to 0, it is 1 equals to this. Say for example, for example, suppose function f is a cosine of x1. Okay. Cosine of x1. Then here, this is a cosine of x1. So when I is still how about I is 1? When I is 1, then this is puzzle h, okay? H puzzle x plus k puzzle 1. Power is 1. Okay. So this is h puzzle x and x1. K puzzle 1 f x1. So this is what? This is h and x. Yeah. Plus k f 1. Puzzle unity. Yeah. So for this function, puzzle derivative with respect to x is what? Take derivative with respect to x. Then negative sign x1 times 1. Okay. Change. Derivative with respect to 1. Say on this function, negative sign x1 times x. Also, this is I is 1. How about here? I is 2. Okay, 2. Yeah. I is 2. I is 2. What is notation means? Yeah. H puzzle x plus k puzzle 1 square. Yeah. Expand is squared by this formula. A plus b square is a squared plus 2ab plus b squared. Expand. So this is a first term square. So h square puzzle square puzzle x square. Yeah. Then plus 2ab 2 h k ab. Okay. Puzzle x puzzle 1 2ab. and then plus b squared partial squared partial y squared. Yeah. Then distribute function f to all the free terms. Okay. Yeah. All the square partial x squared function f. Then co h k partial partial times partial squared. Partial x times partial y. Partial x partial y. Yeah. And then plus k squared partial y squared. Yeah. Okay. First term takes derivative with respect to x twice. So n x. Yeah. Thank you. And then 2hk. Yeah. Here. Take derivative with respect to y first, then derivative with respect to x. So this is a y x. Actually, when function in this step, it can be put take derivative with respect to x first, then to y. It is equal to take derivative with respect to y first, then x. They're the same. So the order, derivative order doesn't matter. When function is the same. Okay, now here k squared, then derivative plus again. So this is I is 2. Very simple. When I is free, then multiply on this power, expand the power, then apply everything to function x. Yeah. This is a Taylor's freedom in 2 variables. Now, finally, let me present Taylor's freedom in k variables. Taylor's freedom in k variables. Very similar. Now this time, k variables, then we consider the theorem in RK, not just R squared. Taylor's theorem in K variables. Let omega be an open rectangle in RK. In R3, omega is a rectangular box. In R3. In R4, we cannot count omega. Okay. And then function f from this set. Yeah, from this. Then from omega arbitrarily take 2 points. Then x1, x2, dot, 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 xk, and x1 plus x1, x2 plus x2, dot, 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 xk plus hk be 2 points from omega. Okay. Be 2 points from omega. Right. Then we have the following Taylor expansion. Yeah. Function value at x1 plus x1, x2 plus x2, dot, 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 xk plus hk. Yeah. I can expand this into polynomials. Summation I from 0 to n, 1 over I factorial. Then times h1 partial x1 plus x2 partial x2, dot, 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 hk partial xk. Then the power is I. Very simple. Apply this to function n, x1, x2, dot, 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 x. Then plus error, e, error, plus error. Then the error is also rare, also very simple. Error is equal to 1 over n plus 1 factorial. h1 partial x1, partial hk partial xk. Now the power n plus 1. Yeah. Then apply this to function n. Okay. No. Expansion. Then apply the operation to function n. After we get derivative, part number. Okay, here, part number. Which number? Yes, here. Part this is x1 plus data h1, x2 plus data h2. Same data. Xk plus data hk. Where data, not much information about data. We know there is such data, so that this equation is true when we add the error. We know data between 0 and 1. Okay. This is what we know only. Okay. Data between. This is Taylor's theorem in K variable. In 2 variables, we will use. Okay, we will use in later start. I'm done with section 1.1. Now we turn to section 1.2. orders of convergence. Second topic, section 1, 2. Orders of convergence. Suppose we have a sequence of numbers. Okay. X1, X2, X3, and Xn, general term, and so on. This sequence converges to some point. Yeah. Converges to some point. Yeah. Now, orders of convergence measure how fast this sequence converges to the point X star. Let me show you one example. Yeah, take a look at one example. Example 1, consider the following three sequences. Consider the first sequence, xn, okay, general term, xn. Xn is a 1/1 plus lateral log n, general term. Okay. If we expand this sequence, the first term, n is 1. N is 1. First number. It is a 1/1 plus lateral log of 1. Yeah. First number. Second number, n is 2. N is 2. Yeah. 1 plus lateral log 2. Third number, part in number 3 in n to get third number. Yeah. This location is sequence. Now the second sequence. Let me call the second sequence XYC. Okay, 1. Okay, 1. General term 1/n squared. If I expand this sequence, n is 1, then I get 1/1 squared. It is 1. N is 2, 1/2 squared. N is 3 squared, and so on. The third sequence is, let me call the third sequence C. General term 1/En. Yeah, general term. When n is 1, 1/e. N is 2. Yeah. It's easy to see that these three sequences all converge to 0. Yeah. This is a 1/1 plus n. Yeah. Converge to 0. That's n. The second also converge to 0. Easy to see. All the three sequences converge to 0, but at different rates, at different rates. How to see different rates? Make a table. Make a table. Okay. Let me erase here. Make a table. Then we will see which one converge to 0 faster. Yeah. The first column for n, and let n go to infinity. Second column for xn, 1 minus 1 plus ln n. Yn is 1 over n squared. Cn 1 over En. Okay, now pick some numbers for n. N is 1. Okay, then 1. This is a 1 over e. 1 over e on 39, 36, 78, 79, 4, 4, 1, 2. Our n is 2. Calculator. 0.5906161 and then 0.25. 0.1353352. How about n is 10? Then a 0.01. Oh, this is a 4.53999,298 times 10 to negative 5. Yeah, you see the sequence Cn converges to 0 very fast. How about 20? 0.250267. 10 to negative 9. If I take, say, one more number, say, at 200, see what we got. And this is a point 15, 87, 7, 25, 6, 4. And here, 2.5, 10 to negative 5. How about 1.3838965. 10 to negative 87. So when n approaches infinity, yes, all the three sequences approach 0, but at different convergence rates. Now, how to characterize the convergence rate? I introduce definitions. Suppose we have a sequence that converges to some number. Suppose we have a sequence that converges to some numbers. Okay? To some numbers. Okay, now definition. Okay. Hey, if xn plus 1 minus x star take absolute value. This is distance xn plus 1 and x star, the distance between these two numbers. Take absolute value. If let me call xn plus 1 the current term. Okay. Distance of the current term to x star over the distance of series term from x star. Okay. Yeah. Yeah. This is a reason. Take limit. If this limit converges to some number c, where c is between 0 and 1, then in this case, we say that the sequence converges to x star linear. In other words, if this condition is satisfied, then the sequence, the convergence rate is linear. Linear actually is not fast. Yeah. Actually, yeah, here, the sequence is converged to 0 linear. How? Have a check with this limit again. Yeah. Say for example, yeah. Let me erase. It looks very fast. It turns out that quite slow. Okay. Just a linear convergence. Yeah. Let me have a check. Let me compare that limit. Yeah. Limit n approaches infinity. Now, Cn, this sequence is converging to 0. Okay, so x star is 0. So minus 0. Plus 1 minus 0. Then over Cn minus 0. Let me compute this. So this is a limit n approaches. Okay. Cn plus 1. It is 1 over E n plus 1 minus 0. Absolutely. Okay. 1 over n minus 0. Yeah. Now, simplify this quotient. Okay. Simplify. Clearly, positive number, so I can directly remove absolute n over E. And now, this En, I can move it to the top. And this is a En over En plus 1. How? Okay. Now, cancel out En. N approaches infinity, 1 over E. So the limit is 1 over E. Yeah. 1 over E. Yeah. Satisfy this condition between 0 and 1. E 2.8 something. 1 over E less than 1. So this is the test. So therefore, this convergence looks very fast. Actually, just a linear convergence. Convergence. Not very fast. Yeah, we have many examples. Linear convergence is order 1 in convergence. we have order 2, order 3, order 4 convergence. This is definition 1. Compare the current distance with the previous distance. Then take limit. If the limit between 0 and 1, then linearly converge to x star. Now, B. B. If this limit xn plus 1 minus x star, I call xn plus 1 current term. Current term, the distance to x star over the previous term, the distance of the previous term from x star, then compute limit. If the limit is 1, not just between 0 and 1, this case, we say that, and we say that the rate of convergence of this sequence is worse than linear, lower than linear. An example? Yeah. In example 1, I'll show you 3 sequences. The sequence about C, linear convergence, the rate. The first 2 sequences, actually, they are worse than linear. Yeah, let me show you. Yeah. What is the xn sequence in the example? Take a review. Xn is 1 over 1 plus vector of n. If this go to 0, yes. How fast? Let me compare how fast. Xn plus 1 minus 0, absolute value. Xn minus 0, absolute value. And today, let me compute this. So, I can remove absolute value because easy to see. Okay? Xn plus 1 minus 0 is possible. So I can remove 1 over 1 plus Ln n over n plus 1. Okay? n plus 1. Then 1 over 1 plus Ln n. Okay. Now move 1 plus Ln n to the top. Yeah. Yeah. Good. It's done. Here, the top. Okay. Yeah. So this is a limit n approaches infinity. At 1 plus Ln n. 1 plus Ln n plus 1. Okay. Do you know how to find this limit? Any idea? From calculus. Calculus 1 is sufficient, okay, to find this thing. Do you know how to find? Any idea? Divide? No. Yes. Divide everything by Ln n. Yeah. Then let me see. Try again. Ln plus 1. Then 1 over Ln plus Ln plus 1 over Ln. Yeah, maybe it works. Okay. This clearly approach 0. And this approach 0. How about this? This should approach 1, I believe. So the whole thing, the limit is 1. L'Hopital's rule better, actually. Yeah, L'Hopital's rule. Okay. Take derivative with respect to n. Yeah, L'Hopital's rule. Yeah. Actually, in my notes, I use L'Hopital's rule. But yeah. Yeah. So L'Hopital's rule. Yeah. Take derivative. Okay. Yeah. With respect to n. Yeah. Then this is a 1 over n, the top. The bottom is a 1 over n plus 1. Right. Now, move this guy to the top. Then I get n approaches infinity, n plus 1 over n. So this is a limit n approaches infinity. 1 plus 1 n. So the limit is 1. Right. Yeah, x. The convergence rate worse than linear. So from the table, I have erased the table. From the table, you will see x, the sequence, converge very slowly. Y also very slowly. The sequence Y in the example, the convergence rate also worse than linear. C, the last sequence, converge fastest compared to free sequence. Okay. Okay. It's 1. Okay. Then definition C. Okay. C. Yeah. This is definition B. Definition C. C. If xn plus 1 minus x star absolute value over xn minus x star absolute value. Take limit. In definition A, this limit between 0 and 1. Definition B, this limit is 1. Now, the limit is 0. Okay? This case, we say that the rate of convergence of the sequence is between 0 and 1 linear, not super linear. A super linear. In this case, super linear. Any example about super linear? I don't have such an example in my notes. Okay. So, yeah, if a sequence is super linear, then the sequence should be faster than the C sequence in the example. Super linear. Okay, now the rate of convergence is quadratic. Okay, quadratic convergence. Right? Right. Convergence. Right. Here. D. D. Okay. Quadratic convergence. D. Right. Linear. The power in the denominator is what? Linear. Now, quadratic here, the power is 4. Usually, because xn converges to x star. So when n is large enough, xn minus x star should be less than 1. So this is a small number. X squared, even smaller. Now, the current distance compare the even smaller number converge to this time converge to C. Where this time C is not required to be between 0 and 1. Yeah. Between now this time here, between 0 and 1. If this is true, we say that the rate of convergence of the sequence, the sequence xn is quadratic. Quadratic is for jet. Yeah, we will learn, in data chapter, we will learn how to solve a general equation. Yeah, the function is a general function. How to find the root? Yeah, how to find the root? There is a method named Newton's method to find the root. Newton's method, the convergence rate is quadratic. I stop here, and see you Friday.